What you're being asked to do is lift and drag. The other one will be side force. So I'm asking you to identify the force in the x direction, the force in the y, and the force in the z. For this one, we've got x in the direction of flow, so that becomes my drag. We've got y perpendicular to that, so that's going to become my lift. Okay, I'm assuming this is a 0 degree one in that sense. Remember that, be very careful with this one. When you get to 5 and plus or minus 5, remember it's the direction of the flow that is drag, not the axis. So if you've got flow sweeping in here at 5 or 10 degrees, that's the direction of drag, and lift is perpendicular. Okay, so for 0 degrees it's easy, it's just going to come along there in the x direction. Y perpendicular to it is going to be lift, and my z component is going to be side force, which to be honest I'm not really interested in and should be small. So the question that you've been given is, tell me what the lift, the drag, whatever coefficients are as a number of angles of attack. Because at subsonic you're going to compare them with the book, Abbott and von Dernhoff, and they have lift and drag coefficients. Transonic and supersonic, you're on your own. If you can make it work with subsonic, then we could assume that you're doing well with transonic and supersonic as well. So what you do on the force is, it says tools, function calculator, change area to force. Say where it is. Now this is good because this has got the aerofoil into 2 sections, so I can either keep it that way, or for the moment I could hold the control down, pick the other one. Oh no, I take it back, it doesn't take it back, so I'll take over one of them. Right, so this is the lower part of the aerofoil, x direction, that means that's my drag in that sense. So x direction, interesting. Right, so I've got a negative, it's negative drag because it's 1. If I do up 1, okay, add the 2 together, overall it's positive. Right, so it is, are you okay with that? So I got 1 value on the lower surface, 1 value on the upper surface, both of them in the x direction, add them up, gives me my drag on the aerofoil. If I change that to y, it would give me my lift. Now, if you look at here at the solver with the funny little lines, there's 2 things which are particularly useful. When the iterations finish, first of all it gives you the domain imbalances, the ones I keep waffling about must be less than 1%. So that's plus or minus, but plus or minus less than 1%. And you can see all these are very good. But it's the next bit which is really interesting, because that gives me pressure force and viscous force. So in other words, on my aerofoil up here, it's given me the x values, so the drag, the y, the lift, z, the side force, due to the pressure. And the one down here is the skin friction. Add the x component and the x component together, pressure and viscous, and I'll get the same answer as I did before. But this one tells me how much skin friction there is against how much pressure. Okay? Right. So that is your lift and drag. You have to convert it to a coefficient. Remember, that's a half rho free stream value, u free stream value, irrespective of angle of attack. It's always the free stream value, the value you got from converting from the Mach number or the Reynolds number. And so half rho u squared, and the area, the planform area, is the chord times the little thickness there, and when you're in 3D it will be the half span of the wing.
So do you have to do that for subsonic as well? Because that's incompressible flow.
Yes.
Doesn't have a place in the equation.
Of course it does, yes.
Is it?
Of course it does, because otherwise I wouldn't have, if I haven't got a half rho u squared s on the bottom, I would have a dimensional number, and it must be non-dimensional. S, the planform number, is making it non-dimensional. So a half rho u squared s is the same dimensions as force. So they all have planform area in. Right, that's the first one. The second one you're asked about is the CP plot. Why? Because we want to see, not if it's got lift, we know that from these force calculations, whatever. We want to see where the lift is. Now, you've already got them in that sense. You already know what you're doing. What we're doing is we're going to take what's called a polyline. This isn't a simple straight line. So I go to location and I choose a polyline. Now, it says from a file, no idea, but I do know that that aerofoil is sitting on both the wing, by definition, and the symmetry plane. So if, in this case, it's a good idea to do, if you've got the lower surface, do it separate. You can see here, this is what you get, a red line and a blue line, and they're easy to see. But I'll do this all in one go. I'm going to do the upper and the lower aerofoil intersecting with a symmetry plane. And then, if you notice I've got this sort of vibrant green line, that's my polyline. There is a little icon up here, which is a graph. If you then click on that, the data series is a polyline. Now, that's not what we're looking for yet. Now, the x-axis is chart count, which is just the recorded in the order that they did it. In this case, we know that it's the x direction we want. So that's what we're going to put x in. The y says pressure. Remember in this code, pressure is P minus P infinity. So it's the change from the free stream, and that's exactly what we want. Now, you'll recognise it more if I invert the axis. So I've got basically the negative one. The only thing that requires now is I can export it, and I must divide by a half rho u squared, free stream values, to make it CP rather than just a pressure difference. At the moment it's in pascals, I must divide by dynamic pressure to get it as a non-dimensional number.
So when you export it to Excel, you divide it by the half rho.
You will have to do it, because at the moment it doesn't know. I could make, you have the chance here to make a variable and things like that, but if you, it would be easier for you to just export it to Excel and then divide every single point by a half rho u squared, all free stream values. And you'll end up with a plot exactly like that. No, because pressure, force is pressure times area, so pressure is referenced by dynamic pressure, force is referenced by dynamic pressure times area. Okay? Right. Now, we actually need, okay, if we want to know where the separation is, this is what I suggest you do. It probably doesn't work for this one that we've got, but take a symmetry plane, and it might be easier if it's 3D. Has anyone got a 3D, a wing, or a very large aerofoil? Yeah? Right. I'm going to transfer to that one because I want to show you how to do something for a wing. Right, here we go.
I've done the result yet.
Yeah, so, doesn't matter. As long as we got a results one in there, have we got a results one to do with this? Have we got a results? Oh, I don't know. Wait a minute.
Sam, have you got results?
Not really, because I changed something. Abby's got it. But
Abby?
Yep.
Have you got... Right. Anyone got a 3D? You've got... I'm on a 3D
I've got results for one for the previous one.
Yeah.
Jesus Christ.